Hi everyone, my name is Samuel Abrahami, and today I will be giving my presentation on my research topic of the Markov chain Monte Carlo algorithm. So for today's agenda, I will have to go over a few prerequisites in order for us to fully understand how the Markov chain Monte Carlo algorithm works. With that being said, I will first go over the Monte Carlo algorithm, and that will after that we would have the Markov chain algorithm, and something else which is really important is the Bayes theorem. Once we have all those prerequisites down, we could go into the topic of the Markov chain Monte Carlo algorithm. So for the Monte Carlo algorithm, without going too in depth about it, the goal of this algorithm is finding the approximate value of a expected value that you're looking for. The way this is done is by generating random numbers, and through these random numbers that you generate, you can get the approximate expected value that you want. This is done by, we would take the sum of the number of values that are within the parameter that we are looking for, and we would divide all of them with the sum of all the random values that were really computed to find this expected value. I will be showing you how this is done with a quick. Suppose you wanted to find the area of the circle and we didn't really have a really good idea of how to really find this area. But within this case, technically speaking, you would be able to find the area of the circle because you have the width and the length of the square. So if we did the calculations of it, we could say it would be 78.5 square inches, the area of the circle. However, let's say we wanted to do it in a different method. We wanted to do this by doing some random sampling of generating random values. And we could try to find the value of the area of the circle. So let's suppose that we generated 20 random values, as you could see here in this entire picture I've shown you guys. I've generated around 20 different values inside of this entire picture. We would have 15 of them that randomly got selected within the circle, and 5 of them did not get inside of the circle. So based off of Monte Carlo's algorithm, what we would do is we would take the sum of the values that were inside of the circle, which in this case it would be 15, and we would divide all of this by the sum of all the values that were plotted. So in this case, we would have 20 values, meaning we would have 15 with inside of the circle and 5 that were outside of the box. And if we did a calculation of this, we would see that the estimated value we got is 75 square inches, and we could see that our expected value, it was 78.5 square inches. So what's really amazing about the Monte Carlo algorithm is that you're able to find out the expected value by generating random values. The next topic of this presentation goes into detail about the Markov chain algorithm. This algorithm, it goes through a sequence of events that are probabilistically connected to each other. So in a sense, what's really going on in this algorithm is we're trying to find out if you're in this certain chain, what's the probability of going to this next area? And it's just a really of a chain of events. And the next point is really saying what I just said. It's saying how each state comes from a set of outcomes, and each outcome determines which outcome occurs next, according to that fixed set of probabilities. This may sound very strange, but when I go to the next slide, it will be much more clear once I show the example. And something else to know about the Markov chain algorithm is that the Markov chains are memoryless. So what this means is that the current chain that you are on is what really only matters. The previous outcomes that happen are meaningless. It only is really important to where you currently are in that state, or you want to call it in that chain. A really good example of how the Markov is really of a famous board game that I used to play as a kid. It's called Chutes and Ladders. The goal of the game is where you start from square, which is in the bottom left corner, and your goal is trying to reach to the 100th square, which is in the top left corner. In the game, you're gonna have like ladders that can allow you go up to, which will get you quicker to the 100th square, and there could be chutes, which make you go down less. So the game is done by rolling a dice. So, for example, like each time you roll the dice, let's say I rolled a 5, right? And I got on the fifth value over here. So what the current state I'm in is what's only important. So to make this more interesting, let's say I rolled again and I got let's say we got all the way to the value of the 26, right? So all the previous squares or all the previous cases that happened are meaningless. In a sense, they're memoryless. We only care about the current state we are in, which means is that what values do I have to get on to get closer to this 100 square. So the probability of is for me to get a 2, which will get me really up the ladder all the way to the 84th square. Or if I get another value which is giving me a shoot, and that can make it much worse. So the whole point of the game that I'm trying to make with Chutes and Ladders is that it's very similar to a Markov chain, because it's only important about the current state you are in to find out the probability of each current like area. And if you were to kind of simulate through this entire board game, you would be able to find out the probability of every single type of a chain you are in, or in any state, because of how many times it's been going on. So that's what's really nice about the Markov chain. You're going to be able to find out by doing multiple runs of the simulation the probability of the current state that you are in. The next prerequisite, and the final one I should say, is Bayes' theorem. What Bayes' theorem is about is trying to find out the most plausible type of model of our original case. In order for me to explain what I'm talking about, I have to first go over some terminology. So the first thing is we have to know what a model is. It's pretty much we create possible scenarios of the original case that we are in. The next on the terminology is the prior distribution, which is the plausibility of each model before we actually reveal any real data. And the next vocabulary word we need to know is the likelihood, which is the hypothetical probability of each model. So in a sense, what we want to know is based off all the models we created, we have to say, okay, this is the probability of this happening in the original case based off of this current model. And the last area is the posterior, which is the plausibility of each model after observing some data. I know that this may be a bit confusing to understand at first, but once I bring in the example, I hope things to become a lot more clear. So let's say we have a bag of marbles. And there's 4 marbles inside the bag. However, all we know about this bag is that there's 4 marbles inside, and they're either red or green. So, and this is the original case that we have, and we want to know what is exactly inside of this bag of marbles. So with Bayes' theorem, the first thing that we would do is we would create the models. So with this case, we could create 5 models, with one being 4 marbles are red, or 4 marbles are green, or 3 marbles are green and 1 is red, or 3 are red and 1 is green, or 2 are red and 2 are green. So these 5 cases would be our models. The next step of Bayes' theorem is finding out the prior distribution. So based off of all our models, since we have 1 models, there's a 1/5 chance of these being the correct model for our original case. However, these aren't really good like examples to use because these are the prior distributions where we don't really have any data, actual data of the original case. So all we know so far is that they're all evenly plausible of being the original bag that we are looking for. The next step of the algorithm is to find the likelihood of each model. So what we would do here is we would try to find the hypothetical outcome of each model, and we would do some testing over it. So in this case, let's say we did 100 tests of each bag, and the outcome would be for the probability of each one would be for the red, it would be 100% chance of only getting red in the first model, which is obvious, and also for the second one it would be obvious only 100% chance of it to be green. And the third model, we could see here that there's a 75% chance of it being green and a 25% chance of it being red, and so on with the other two models. So with the likelihood, we're just trying to figure out what's the most likely outcome of the original case that we're trying to find based off of these 5 models that we currently have. Now we're up to the last step of Bayes' theorem, which is the posterior. Now we go to the actual original bag that we have and we do some observing of the data. So let's say we put our hand in the bag and we took out a marble and we saw that it was green. So based off of that, we could already eliminate, which you don't see here anymore, is the 100% red bag, because that is not plausible at all. Based off of this first experiment, we could say that the 100% green one is the highest plausible, and then the 75 green and 25% red bag is the second plausible, and so on, based off of the first experiment that we did. Suppose we did the experiment again. We put the green marble back in the bag and we shaked it up, mixed it, and we chose out another marble, and it became red. Right away, we would eliminate the other model that we had, which was all green, because that's not possible. And we could see here now that the most plausible model would be the bag with 50 red and 50 green. And hopefully, by observing what's going on so far, if we did this for multiple runs, we would be able to figure out what's the most plausible model based off of running Bayes' theorem. And that's what's really nice about this whole case of Bayes' theorem, is that you could figure out what's the most plausible model of the original case without knowing exactly what's inside of it. So the formula of Bayes' theorem, based off everything I've explained already, would be that the posterior would equal to the likelihood times the prior, all divided by the probability of the data. So everything that I just showed you from that example, this would be the formula of how everything is calculated to find out what's the most plausible type of model. Now that we have all the fundamentals down for the Markov chain Monte Carlo algorithm, we could now go into conversation about it. So MCMC, it's a very similar concept to Bayes' theorem. We're trying to find the posterior. However, with MCMC, we're dealing with complex distributions where we're dealing with a much more advanced and difficult type of process. And what Markov chain Monte Carlo does is it breaks down this distribution into like simpler parts, and we would try to figure out the outcome of those. And in this case, it would be the likelihood and the priors, similar to Bayes' theorem. However, what's different from Bayes' theorem is that we're going to combine them together, the simple parts, and to make them into a complex outcome. So the best way for me to really explain this is by showing you an example of a Markov chain Monte Carlo. So in this example, we have two people. Call them Bob and Alice. They wanted to do an experiment and see how they can get onto the top of this hill. So the experiment was that they both start at the bottom of the hill and they would flip a coin. And if when they flipped the coin, if it landed heads, they would take one step up, which is the more plausible method, or I should say model, because they are trying to reach the top. And if for the next iteration they would flip the coin again, and if it was to land tails, they're supposed to take a step down. However, before taking the step down, they would flip the coin again, and because it's the less plausible type of way. And if it when they flip the coin again and it landed tails, then they would take the step down. But if it landed heads, they wouldn't make any type of movement, and they would just do the next run of this like situation they're trying to do. So if this was being simulated for many iterations, majority of the time, Bob and Alice would be at the top of the hill because, as you could see, the more plausible method has a much higher chance of happening than the less plausible method, which requires a double flipping of the coin. So this is the same idea of a Markov chain Monte Carlo algorithm. You're dealing with a chain of steps within the parameter, in this case being the hill that it's going on. And what's really interesting about the Markov chain Monte Carlo algorithm is that there's many different type of algorithms for it. One of them, which is known as the Metropolis-Hastings algorithm. So the Metropolis-Hastings algorithm is an example of the Markov chain Monte Carlo algorithm, which was exactly the exact example that I just showed you in the previous slide. So what's interesting about the Metropolis-Hastings algorithm is that you're dealing with two areas, the proposal distribution and the acceptance probability. And what we're dealing with here is, in the first step, is the proposal distribution. When Bob and Alice, they had to flip the coin, they wanted to see if their proposed model is a much more plausible model than the previous one. Which, if it was, then they would stick with that model. Meaning, if they were to flip the coin and it landed heads, they would take a step forward. However, if they were to flip the coin again for the next iteration and it landed tails, which is less plausible than landing on heads, they have to figure out the acceptance of probability, where over here they're going to have to flip the coin again for that iteration because you're dealing with a less plausible proposed model. And if it was to land the tails again, they would take the step back. But if they were to flip the coin and it landed heads, then they wouldn't make any movement at all. So that's what's really nice about the Markov chain Monte Carlo algorithm. You're kind of manipulating the more plausible type of a model by making you having to do the acceptance of probability, which allows you to find the posterior distribution much more easier. In conclusion, the Markov chain and Monte Carlo algorithms, including Bayes' theorem, really create the Markov chain Monte Carlo algorithm. It allows us to take complex distributions and break them down into simpler parts and pretty much put them back together as a complex outcome and help us to find the posterior distribution that we are looking for. Thank you so much for listening to my presentation and have a wonderful day.